So this is our sample problems, no, in relation to finding density, finding maybe now later on the specific gravity, and we realized that pressure, density, specific gravity are some properties of our confined liquid, no, or gas. So these are ways that we can determine our our fluid. No? So identifying them, no, is one way of identifying them is using our concept of density. So again, we have here now our given value. No? So we are given the diameter of a spherical ball. No? So in order for us to find no, the density, then we need to divide the mass density by the volume of the object. So if the object here is a spherical ball, then we will use the formula for sphere no, to be able to find its volume. No? So that's the first thing that we'll probably do. No? So in our solution, we need to find out the formula or the value for V. And V here is our volume. No? So volume for our sphere is 4/3. Then we multiply it with pi. Then we will multiply it with our radius. No? So multiplying it with radius. And we raise the radius to the third power. We cube no, the radius of our formula. So that's 4 pi no, r cubed. No? And again, that's how we calculate the volume. No? So again, our volume will now be 4/3, then substitute pi. And pi now in your calculator is around 3.14. Our radius will be half of the diameter, which is given to be 2, no? So half of therefore 1, no? 1 centimeter. And we cube that, no? Therefore our volume will eventually be expressed in cc. So that's cubic centimeter, no? So what we mean earlier no, by cc. No? So how much is our volume? No? Pila natin volume. So again, our value now no, is this one, no? 4.19 cubic centimeter. No? Assuming that that's correct, no? So you can either write cc no, for this value. So cc stands for cubic centimeter or cm cube. No? Now, if we will now find the density or the mass density. No? So mass density again is symbolized by small letter d. So small letter d is equals to m divided by v. No? And v again is volume. So mass being 30 grams. No? So we have 30 grams there divided by a volume of 4.19 cm cube. So how much will be our answer? No? So again, the unit here is, by the way, cube. No? This is cubic centimeter. No? And again, we are dividing the expression there. So how much will we have for our answer? No?
7.16, sir.
Eventually, when we divide 30 grams by 4.19 cubic centimeter, we have 7.16 gram per cc. Cc for cubic centimeter. Any question with number 1? Okay, we start with number 2. So number 2 is a tin can has a diameter of 10 cm cube as 10 centimeter and a height of 30 centimeter. It is filled with sodium chloride, NaCl. If NaCl has a mass of 2,400 grams, or if you make it in kilogram, that's 2.4 kilograms. So we will find the density. I think what we are looking for here is the density of the NaCl or sodium chloride. So we are not looking for the can. However, now the sodium chloride is placed in that particular can. 2 now again. So the NaCl's volume is not given. However, the container that holds it no, is in a form of a cylinder. No? And this is the dimension of our cylinder. No? Diameter, height no? Is provided. So what we want to find no, in this problem, we want to find the density D no, of our NaCl. No? So how much is the density of our NaCl? So first of all, to find the density, no, we need to find the volume no, of our no, volume of cylinder. No? So if we fill no, the entire container with our cylinder, no, kung ginpuno ta na sa, then our formula for the volume of a cylinder is pi. No? Then we multiply it with the radius, and we square the radius. No? So pi times radius, no? And sorry, no, that's radius. And we multiply the square of the radius, no? So actually, ang radius is squared na, and then multiply ito siya sa height, no? So we multiply it with the height, no? So there are three values that we will solve there, no? So the radius again is being squared, no? So we square the radius. In the volume of a sphere, we cube it, no? So that's the standard volume of our sphere, no? Or our cylinder. No? So therefore, this, if we will substitute this, no? So if the diameter there again for number 2 is 10, no? So we will have here pi, no? First of all, pi multiplied by 5, no? 5 centimeter. That's the radius, and its height, no, is equals to 30 centimeter, no? And our value there will eventually become, no? Our value will become cubic centimeters still, no? So our volume for this given number is how much? No? So again, eventually we will have here, no, our cylinder, no? The volume of our cylinder to be this much, no? 2,356, no? 0.19 if we multiply the given, no, based on our formula, no? So if the diameter is 10 again, the radius is half, no, of 10. So that's why we have here 5 cm, no, and multiplying it with the height. No? Now we are ready to find the density D. No? And again, D is M, no? M divided by volume. No? So we will be dividing M by our volume B. No? So that's how we determine, no, our density. No? So mass is given to be 2,400. No? So you will have a value here, no, equal to 2,400. Then we divide that with 2,356.19. No? So this is in cc, while our numerator is in grams. No? So eventually our answer, no, for density will be gram per cubic, no? Gram per cubic centimeter, no? Or cc man gyapon ang denominator. No? So how much is our density? No? So our answer again, no, is 1.02 gram per cc. So basically this is the density of sodium chloride. No? I think this is a seawater. No? The NaCl that is probably referred to this one, no, is the NaCl solution. No? So manotice ninyo, no, if you are in seawater, no, seawater is quite heavier compared to fresh water. No? That's the reason why we float more, no, if we are in seawater, no, because there's salt that is dissolved there. No? So therefore we see that this NaCl probably solution, medyo taas lang siya gamay sa tubig na density. No? Because water has a density of exactly, no, 1 gram per cc. No? So this one, no, medyo taas lang siya gamay. No? So again, no, this is our number 3 given. So we are given a liquid that is oil. Oil is lighter than water, so it has a density merely of 0.7. No? So the container is only 1/3 full. So maybe, no, the height here of the oil is only 1/3 the dimension, which is basically amo lang eh, no? This must be your oil here, no? Maybe now this is the oil, no? This is only around 20 centimeter in height, no? But this is your container, no? The entire container is 60 centimeters high, no? Now, how much is the pressure at the bottom? If, no, that's the height of your oil, no? So we know that if we find the pressure, no, our formula for pressure is density, no, gravity, and height, no, ang aton formula, no. So G there is the acceleration due to gravity, no. So if the density of oil is 0.7, that's 0.7, no, gram per cc, no. And you have your acceleration due to gravity, no. So your acceleration due to gravity is sorry, no, it is in 9.8, no, but 9.8 is in meters, no, per second square, no. So we have different units here, no. So there must be a way of converting our units, no. Dapat i-change natin unit to be consistent, no. And we have here a height that is also in centimeter, no. So therefore we need to, I think, no, convert that to meters, no, so that we will have a consistent unit, no, in MKS system, no. Once we now get the equivalent, no, unit of the density, no, in kilogram per cubic meter, which is 700, and the height now, which is around 0.02 meters, no, dividing 20, no, I think by supposedly by 100, no. So if you divide it by 100, it's not 0.2, no, but it is it's not 0.02, no, but ideally dapat it's just 0.2, no, 0.2, no, meters. So therefore, if we substitute now this value for our density, no, so we'll have here 700, that's kilogram, no, per meter cube. Then the acceleration due to gravity, which is 9.8, no, meters per second square, and then our height now, which is 0.2, no. Can you give me the product for these three values?
1372.
So Pascal, guys, no, is a unit of pressure, no, and this is the product of 700 times 9.8, no, times 0.2, no. Now sometimes they just simply write that with PA, no. So the pressure at the bottom here, no, is equals to 1372, no, PA, no. So that's a unit of pressure, no. Usually P is written with capital letter, no. Now, the other question here, no, what part of the container must be filled with water to have a downward pressure, no, equal to that pressure exerted by oil, no? So if we will have to find, no, how high, no, is the water that we are going to put, no, in a similar container, like for example, no, I will get a container here, no, and this one, no, I want to achieve, no, the same amount of pressure at the bottom, no. How high should the water be, no? So if this is for oil, this is the pressure, no, created by oil, no. How high must my water be, no, para nga mag-parehas ang iya pressure, no? We realize that water is much heavier, so maybe now we will have a lesser height here, no, if we will fill this with water, no. So assuming that we will have water here, no, maybe our water will have a lesser height, no. So how much is the height here of this water that we will fill this up, no? Now that is if they have the same pressure. So if we will solve for height, no, height must be equal to pressure, and then we divide it now with the density, no, value. So if pressure is dgh, so ang atong denominator will just be simply d and g, no? So pressure will be divided by d and g, no? But this time the density that we will be using is not that of oil but of water na. So the pressure is the same. We'll have 1372 PA na, Pascal. But our denominator na, we will make use of the density of water, which is 1,000 kilogram per cubic meter. And we multiply this now with 9.8. So 9.8 is our acceleration due to gravity. So multiply that now and divide it to 1372. So how high is our liquid if we have this? Lesser than the one that we saw for our oil. So oil needs to be 20 centimeter or 0.2 meters, but our water will only be 0.14, much lesser in amount. Okay, so again, the reason why we have a lesser height there, but equal in pressure because oil is less dense than our water. Okay, for the last number, for the last item, so we have an object. So let us try the last item or the last number in our hydrostatics question. And definitely, this must be about applying how we use specific gravity and even including the concept of the Archimedes principle in the loss of weight method. So the Archimedes principle is has a wide range of application, and this is how we will probably use this. So we are given here an object that weighs 350 grams in air, 290 grams in water, 294 grams in oil, and 285 grams in sulfuric acid. So we have three different liquids where we will be submerging an object. Maybe this is some kind of a metal or whatever. But this has a weight in air of 350 grams. Now, what we want to determine is its density. The density of that unknown object. So we want to find its density. Then we want to find the density of the oil, and including the density of the sulfuric acid. Now, we don't have to find the density of water because the density of water is already provided. Now, to find the density, so first we will apply the knowledge that we know for the specific gravity. Now, in specific gravity, we understand that if we apply the Archimedes principle, then applying or finding the value of the specific gravity, we can actually divide two different masses. So the mass of the object and the mass of water that it displays. So if you know those two values together, then you can get the specific gravity. Now, however, what we have is the weight of the object in air, which is definitely the mass of that object in air. So if you divide that with the equivalent amount of water that it displaces, then we can get its specific gravity. Then how do we know the amount of or the mass of water that it displaces? Now, in our Archimedes principle, what we know there is that the amount or the mass of the water that it displaces is equal to the volume of the liquid that spills out. So if this one is not collected, then we can still see that the difference of the weight of the object in air by its weight in water will still be its loss of weight in water. So therefore 60 will be the loss of weight of the object in water. So dividing its mass in air, 350 grams by 60, then we get a specific gravity of 5.83. So this object is much heavier than water when we look at its specific gravity. Now, how do we get its density then? How do we find its density? So its density will be the product of its specific gravity times the density of water. So again, given this equation here, that specific gravity is the ratio of two densities, then multiplying the value of SPGR with the density of water will give us the numerator density of the object. No? So 5.83 times 1 gram, no, per cc is now equals to still no the same value with now a unit. No? So 5.83 gram per cc. No? So this is the density of our object. No? Now we will find next the density of the oil. No? But I think it's much easier to find no, its specific gravity before its density. No? So in finding no, the specific gravity of oil, then we get the loss of weight of the object in oil, no, which is actually no, the amount of oil no, that we no, that will be equal in volume no, to the amount of water that the object displaces. No? So you'll notice that in our previous equation, we used this 60 no, as the weight of the object. No? The amount of the loss of weight of the object in water. No? So in finding the density or specific gravity, now this denominator is actually now used consistently. No? All that is changing is our numerator. No? Now, the loss of weight of the object no, in oil no, will be equals to 56. No? And this amount of oil no, that probably spills out or displaced no, is equal in volume to the 60 gram of water. No? So therefore, the ratio no, will now be equals to 0.93. No? So this one is lesser no, than 1. Therefore, no, we say that oil no, will eventually float in water. No? So getting the SPGR of oil no, and multiplying it to the density of water, which is 1 gram per cc, no, will give us no, 0.93 gram per cc, no, which is the density of our oil. No? So again, no, in all these numbers, no, what we see is a common denominator here. No? So this loss of weight of the object in water is our common denominator no, in our loss of weight method in finding SPGR. No? So SPGR now is using the principle of the Archimedes principle. No? So next, no, how to find the specific gravity of the acid. No? So we get the loss of weight of the object in the acid, no? Which is 350 minus 285. No? So the loss of weight in acid is 65 grams, while the loss of weight in water is 60 grams. No? So there's more weight that was lost in the acid. No? So therefore, we have a value here that is more than 1, no? 1.08, which shows no, that the acid is much more heavier compared to water. No? So again, no, getting the density of the acid is to get the product no, of the SPGR, which is unitless, times the density of our water, which is 1 gram per cc. No? Therefore, giving us no, the specific or the density of our acid no, to be 1.0 no, 08 no, gram per cc. No?